Hey, what's up, guys? This is Chung here again. So this time, LeetCode number 1947, maximum compatibility score sum. Okay, so now this time we have a survey that consists of n questions, right? Where each question's answer is either 0 or 1. Okay, and then the survey was given to m students, right? From 0 to n minus 1, and also same m mentors, also numbered from 0 to m minus 1. Basically, each of the students and mentors will answer all of n questions. Okay, and then the student's I is a list of integer which contains all the answers of n questions for the student. Same thing for the mentors, right? And then basically each student will be assigned to one mentor, and each mentor will have one student assigned to them, right? So basically one-to-one relations. And then there's like compatibility score of a student and the mentor pair is the number of the answers are the same for the both the student and the mentor, right? For example, if student's answer is 101, it means that for question 0, the student's answer is 1. For question 1, student's answer is 0. 2 for 2 is 1. And the mentor's answer is 001, right? Similarly for question 0, 1, and 2. And the compatibility score obviously is 2 because only 2 of them are the same, right? And then our task is to find the optimal student-mentor pair to maximize the sum of the compatibility score, right? And we just need to return that compatibility score, right? So for example, so we have 3 students and we have 3 mentors, and there are like also 3 questions in total, right? So the optimal pairing will be like this, right? Where the final answer is 8. Okay, and for this one it's like 0, 0, right? So that's it. And then the constraint is like this, right? I mean, m and n is also only like 8, right? So every time when you guys say the constraints is like only this, like maybe smaller than 10, then it means that probably the time complexity will be like 2 to the power of 10 or 8, which means it's gonna be a full permutation, right? So that's exactly what we're going to do for this problem, because there's no greedy way to optimally assign the mentor to any student. So which means we have to try all the possible combinations for each student against each mentor, right? Basically, what does it mean? It means that for student 0, we're gonna try to assign a mentor from 0 to n minus 1 to the student 0, and then for student 1 we're going to try the same thing, but we have to do it like in a backtracking manner, right? Because once the mentor is gone, we cannot assign this mentor to the other student. That's why this is like a common strategy for like a bit mask, right? Where we're gonna have like a DFS, okay? We're gonna have like DFS where the first the first parameter is going to be the I. I means we're basically now we're assigning the mentor for the current student. Okay, and the second one is going to be the bit mask, right? So the bit mask is what? Is the status of all the mentors, right? Basically, 0 means it has not been assigned. 1 means it's already been assigned. Let's say we have a 0, 1, 0, 0, 1, 0, right? Then it means that, okay, we have assigned this mentor and this mentor, which means only the 0 ones can be used at this moment, right? And with this one, right, this 2 here, we can try all the possible combinations. And then the last one, of course, is going to be the score, right? Right. We're going to also maintain the current score for each of the pair. And in the end, we just maintain update the final answer, right? Whenever we have assigned each student with its corresponding mentor, right, and then we simply update the score, right, to find the maximum one. So that's it, right? And pretty straightforward. And let's do it then. I'm going to call it backtrack, right? So like I said, first I mask and score, right? And so if I is equal to m, okay, we haven't defined the m and n yet. So m is going to be the length of student, right? Basically the same also for the mentors. And n is the number of questions, going to be a number of do we need this n here? Probably we don't even need this n. Okay. Oh no, I think probably we do. Okay. So that's the number of questions, right? Number of questions. Okay, and then for the backtracking, right? So when I reach the end, then we know, okay, we have assigned all each mentor with each student with his mentor. That's when we can update the answer, right? So let's do this. Then local answer, right? Gonna be answer equals the max of answer dot score, right? Yep, and then we return, right? And then for j in range of m, right? So basically for the current student, we're trying to assign student, right? Try to assign all available mentors, right, to student I, right? And we have in total we have we have m mentors. We just need to check if the mentor is available, right? So basically, if the mask, we check if the mask value is 0. Okay, this one equals to 0, right? So a little bit bit manipulation here, right? Then we do a backtrack, right? Backtrack of what? Backtrack of I plus 1, right? And then for mask, it's going to be the mask. We're going to mark that mentor to be unavailable, which means we're going to mark that one into 1, right? That's how we mark it into 1. And then the score, right? So the score will be score plus okay, we need to have another helper functions to get the score, right? So we have student and we have the mentor, right? So answer is going to be 0, and for I in range of n this time, right? So if si is equal to mi, then answer plus 1, okay? Return the answer, right? So here we can simply just call that helper function of students of I, right? And the mentor is of j, okay? Yeah, so that I think that's it, right? And then we can do a backtrack of 0, 0, 0, okay, right? And then return the answer. Yep. Missing one of the required oh, here. Oh, oh, right here. So okay, accept it, and let's run it. All right, cool. So it works, right? Because it can pass because of the time complexity for this one is what? So we have I here, right? So I is like we have n, right? N times 2 to the power of n, right? And then for each of them, we have like what? Each of here we have, oh, then this is going to be another times n for this one and times, oh, we have m and n, sorry. So the I is m, right? The mask is 2 to the power of m. And then inside here we have a m. And then here is another n, right? This one is a O of n. Here is a O of m, right? So that's the total time complexity, I think. Right. And so for this one, do we need a DP here to memorize the result? Probably not. Because I don't think there's any overlapped sub scenarios here because the I always moving forward, right? And every time I is moving forward, the state will be different. So basically, we don't need to store. We don't need to use like DP to store any of the previously calculated results because I is always moving forward. Yeah, I think this is one way of doing it. And the other one is what? I think the other one is we can do a maximum at the beginning instead of updating this one to the end. So what I mean is that, so for this one, I'm passing this score along the way to the end to update the final answer, right? Or we can return this score all the way to the top to update the answer so that we don't have to pass this one a lot in the backtracking. So this is what I mean. So here we don't need the score anymore, right? So instead, whenever we reach the end, we simply return to 0. It means that we don't have any score that we can collect, right? And then here we have answer dot 0, right? And here we don't need this one anymore. Gonna be so something like this. It's gonna be answer equals to the max of answer, right? Here we have this, and then we don't need a score here, right? It's gonna be the mask, and all we need is this one plus, right? This one, and then get score plus the backtracking, right? So this one is this. Oh, we need a okay, right? And then we simply return the answer in the end, right? That's another way of solving this problem. So instead of passing the score along with it, we simply just accumulating the score up, right? We pop it, we bubble it up to the very top, and then every time we do a maximum of that. So this one is this is like a very standard classic DP template, right? So if I run this one, I believe this should also work. Oops. Oh, so and then we can simply return the backtrack, right? Okay, if I run this one, this should also work. Yeah, right. So similarly, and this one, with this one, we can definitely use like a memorization in Python, right? It's going to be a LRU cache, right? None, right? So this is like very standard DP solution, right? With like two-dimensional DP, right? So if I run this one, this should also work. Oh, I think I was wrong about the I was wrong about the scenario, the branches analysis. Okay. Yeah, I thought there wouldn't be any duplicated scenarios, but given the runtime, seems like the DP one definitely runs much faster than the non-memorization version. Let me think. Oh, I see why. Because okay, I think I was totally wrong. Yeah, sorry. Because when if the I, if the first person, if the first person, if first person picked mentor 1 and second student picked mentor 0, right? Or if the first student picked mentor 0 and the second student pair with the mentor 1, then the end result of this I will be the same, right? Basically, and then when we add like when we are reaching the person 2 here, sorry, the student 2 here, we'll end up with the same mask, right? Basically both the first mentor and the second mentor will be has already been used, right? So which means that no, basically, yeah, I was wrong about that. So we should definitely use DP, the memorization version of this backtracking. Actually, it's not a backtracking. I should call it DP here instead. But it does have some backtracking mechanism concept in here, right? So this one should like called DP. Because like I said, both of this branch and this branch will end up with the same state here, right? That's why we should memorize the result for this state, so that when the second branch reaches this state, it can simply return the value, right? That's why okay, correction. For this one we should definitely use this kind of DP version, right? Because like I said, so for this one, the time complexity will be correct. Like the one I said is going to be m times 2 to the power of m, right? And then for here it's going to be m times n, right? So this is going to be a time complexity. This is the one with the memorization, because I think the time complexity analysis for the previous one was not accurate, because they could be duplicated state, right? Or the duplicated branch. Yep, I think that's it, right? I mean, I know the this video is a little bit confusing because of my mistake at the very beginning. I thought we don't need to use DP to solve this problem, but turns out we should use DP instead. And yeah, I think other than that, it's like if we now that I think about it, this is a very like another very classic DP template, where it's a 2D DP state, where the first one is the index, second one is the bit mask, right? And then, yep, I think that's it. And thank you for watching this video, guys, and stay tuned. See you guys soon. Bye bye.